Hello, everyone. It's Mr. Neighbor, and we're still talking about wave speed and how it's related to the wavelength, the period, and the frequency. So all things dealing with wave characteristics. So we have a couple examples in this video. First example is a geological disturbance in California produces a seismic waves, which are detected in Phoenix, approximately 990 kilometers from the epicenter. If the wave or waves travel 6.3 kilometers per second, determine the time delay between the disturbance and the detection. We really don't even need this type of formula for this. If we think about what we want to know, which is the time delay, we're looking for a time, we're given a displacement and a velocity or speed. And really, when you divide 990 by 6.3, the thing you're going to get out is a seconds thing, and you're done. That's all you need to do. 990 divided by 6.3. You didn't need to think about this with a certain formula or anything like that. We don't need to make up a new one. We have one. Just use the one you know. Sorry, that's kilometers per second. If you did want to use a formula, let's think about what one you would use. Well, we know the velocity, so we'll plug that in. 6.3. We know a distance, which would be the wavelength part. So we know lambda. So are we looking for period or are we looking for frequency? Period has a time or an answer in seconds, a time quantity. Frequency has an answer in hertz. So we don't want frequency, we want this one. So we're looking for wavelength, which is 990 over period. When we solve this, that means to multiply the period over, divide the 6.3 to the other side, and again, we're getting 900 divided by 6.3 still. And when we calculate that out, we will get approximately 140 seconds. So that's with sig figs. Otherwise, it's 142.857 if you want that. Next problem, extreme waves along ocean waters, sometimes referred to as freak waves or rogue waves, are a focus of much research and study among scientists. Several merchant ship reports rogue waves which are estimated to be 25 meters high and 26 meters long. Assume that these waves travel at speeds of 6.5 meters per second. Determine the frequency and the period of these waves. So let's plug in what we know. We know the velocity is 6.5 meters per second. We know that the waves are 25 meters high, which would be the amplitude. We don't need the amplitude in either of these equations. And 26 meters long. So 26 meters long, that would be the wavelength. So if I want to find the frequency and the period, I have to plug this in for two separate equations. So 6.5 equals 26 meters divided by t, and I'll solve for t. And then I'll do that same thing again, 6.5 meters per second equals, and now I'll have 26 times the frequency, which I'll solve for the frequency then. When I move things around, it'll be 26 meters divided by 6.5, and this will give us out an answer of 4 seconds for the period. So 4 seconds exactly with sig figs, it would be 4.0, because I need two significant figures. For the frequency, I really can find that quickly since I know the period. It's just 1 over that. 1 over 4 would be 0.25. And frequency is in hertz. So done. If I wanted to, I could take 6.5 divided by 26 to get out the frequency, but you're going to see the same thing, 0.25 as our answer. Last problem. Tsunamis are much different than rogue waves. While rogue waves and other waves are generated by winds, tsunamis originate from geological events such as the movements of tectonic plates. Tsunamis tend to travel very fast. A tsunami generated off the coast of Chile in 1990 is estimated to have traveled approximately 6,200 miles to Hawaii in 15 hours. We want to determine the speed in miles per hour and meters per second, given that 1 mile is 1,609.3 meters. So if we're looking for a velocity, it's just a distance over a time, specifically a displacement. So if we have that, we don't need a formula for it. But notice the distance would be the wavelength, the time would be the period. We're going to calculate it the same way. Surprise, surprise. So let's go ahead and do that. 6,200 miles divided by 15 hours. That comes out to be 413.3 repeating with significant figures, 410 miles per hour approximately. So now I want to convert that to meters per second. I'm going to use this answer to do that. Start with 410 miles per hour. Actually, let me change that. 413 miles per hour. I should be using the precise value, not the significant figures value. I will use significant figures when I'm all done, so I only have 2, but right now I should be using the precise value. So assume I'm using the 0.3 repeating with this. I will do that in the calculator, but I just don't want to write it. So I want to change the miles to be meters. So let's write the equivalent. I need miles to cancel out, so that needs to be on bottom, which means meters has to be on top. So we are given a relationship here that we can plug in. 1 mile is 1609.3 meters. So that's going to cancel out our mile labels. Next, we need to get rid of the hours and get out seconds. So that means if I want hours to cancel out with the hour in the denominator, I need 1 on top, which means seconds will then have to be on bottom. So 1 hour has how many seconds in it? Well, it has 60 minutes, and each minute has 60 seconds. So 60 times 60. That'd be 3,600 seconds in 1 hour. So hours cancel. The 2 labels I will be left with are meters and seconds, which is what I want. So let's do the calculations. 413.3 repeating times 1609.3 times 1 divided by 1 times 300,600 seconds. That gives me out 665,177.3 repeating over 3600. And when I divide that, I will get out my final answer of 184.77 approximately, with significant figures 180 meters per second about. So there we go, the 2 different velocities in miles per hour and meters per second.